So is the presentation visible? Yeah. Okay, so this is actually the eighth week of live problem solving session on Gate Metallurgical Engineering. I am Santara Krishnan, and these sessions are brought to you in association with NPTL and PMRF. So, in the previous 7 weeks, I have recorded videos and uploaded in YouTube. And in case you find time, please go through those questions. And since the exam is nearing, we will be seeing previous questions from past question papers. And many of the questions that we have already solved, we'll be repeating so that you will get an idea of the concept. So, on that note, let us move on to today's session. Since it is only like two of us, it will be like a one on one session. You can directly ask me doubts whenever you feel the concept is not clear. And whatever inputs you have based on the question, I'll be asking you and you can respond. So we'll start with today's first question. That is, if sigma and epsilon are the true stress and true strain respectively, the maximum uniform strain that can be imparted to a material obeying sigma is equal to 1050 epsilon power 0.25 is. So this is the first question. So like, do you have any idea on how to start solving such kind of a problem? Okay, so then I'll go with the concept. So the thing is, here it is given sigma is equal to 1050 epsilon power 0.25. This is a power law kind of relation and it denotes the true stress and true strain. So first of all, this equation tells us about true stress and true strain. So what are the components here? Sigma is true stress, epsilon is the true strain, n is the work hardening exponent or the strain hardening exponent, this particular n, and k is a constant, that is the true value of stress at a true strain of zero point 0.1. It is called the strength coefficient. It is a constant. It will be given. So this is this particular relation here. Sigma is there, k value is equal to 1050, epsilon is given, and n is equal to 0.25. Now we need to find out what is the maximum uniform strain that can be imparted to the material. So first of all, we need to know what is this N. So N, we have told it is the strain hardening exponent or the work hardening exponent. So usually the value of N lies between 0 and 1. 0 means that it is a perfectly plastic solid. That is, when we apply a stress to the material will deform and it will remain that way. It won't come back to its original shape. And if the value of n is equal to 1, it means that a perfectly elastic solid, which means that when we are deforming the material, we will be applying some force, the material will deform, and as soon as we release the force, the material will come back to its original state. And in normal cases, most metals will have an n value between zero point 0.1 and zero point 0.5. So actual value will lie between 0 and 1. So what is the significance of n? For example, if a material has higher value of n, it means that the material has greater capacity for being formed. That is, the material can be put into different shapes if the value of n is higher. Also, if the value of n is higher, the material's resistance to necking increases. So what is necking? Whenever we are deforming a material, it goes on stretching, and at one point a neck will be formed. And after neck formation, when we are giving further stress, what happens? The material will undergo breakage. So this is the significance of n, or the strain hardening exponent. Now we need to find out the maximum uniform strain. So what is the maximum uniform strain? The maximum uniform strain is the true strain up to the maximum load. So this is our normal stress strain curve, right? So this blue one is the engineering stress strain curve, red one is the true stress strain curve. So here, if we can, if you know the engineering stress strain curve, this point will be the yield point, and this will be the ultimate tensile stress, and finally this will be the fracture point. The strain value corresponding to ultimate tensile strength or maximum load is known as the true strain at necking or true uniform strain. So, in case of an engineering stress strain curve, this particular point is called the ultimate tensile strength, and the strain value corresponding to that particular point is known as the true strain at necking or true uniform strain. And from theory, we know that if we have an equation like this, that is K, sigma is equal to K epsilon power n at necking, n value is equal to this n itself. So that is, if we have a case like this, that is sigma is equal to k epsilon power n at a point of necking. At necking, what happens? The true strain at necking has the value of n. Therefore, the maximum uniform strain in the above case is same as the value of n. That is the answer. So, for two things we need to know in this particular problem. First, what is true strain at necking or true uniform strain? They're actually the same thing. That is the value of strain at the ultimate tensile strength. And what will be the value of the strain? It will be equal to the value of the work hardening exponent or the strain hardening exponent, that is the n value. Therefore, maximum uniform strain is 0.25 from the equation itself. So, is this clear? Yeah, so that is the true strain at necking or true uniform strain. Just keep in mind this particular equation, that is sigma k epsilon power n, where n is the strain hardening coefficient. At necking, strain is equal to n. And it has different names, true strain at necking and true uniform strain. So with that, we can move on to the next question. When boron, it is a trivalent atom, is doped into silicon, the resulting material is p-type semiconductor, n-type semiconductor, superconductor, or an insulator. Do you have an idea? Yeah, that is the case. So, how do we explain this? So, this is our periodic, a part of the periodic table, and here we can see that silicon is a tetravalent atom, that is, her four valence electrons are there, and whenever it is doped by a third group element, trivalent atom, it becomes p type, and whenever it is doped by a pentavalent element, it becomes n type. So, how does this happen? So, this is normally an array of silicon atoms, that is, these gray rounds are silicon atoms and the dark black circles are electrons surrounding them. Each silicon has four electrons surrounding them. Therefore, when combining two, on every side there will be having 2 and total of 8 electrons will be there. Suppose we are removing this gray dot and replacing it by boron, say phosphorus, that is a pentavalent atom. What happens? It has 5 electrons in the outermost shell, 4 will be taken, same as to what happens in case of silicon, and one extra electron will be there. Therefore, the number of electrons in this particular configuration has increased. This is why when doped with phosphorus or a pentavalent element, the material becomes an n-type semiconductor. So next is the case where it is doped with boron, that is a trivalent material. So when the silicon atom is replaced by a boron atom, it has only 3 electrons in the outermost shell. Therefore, instead of an excess electron, what happens here? A hole will be there. Therefore, we can say that the number of holes has increased and the material has become a p-type semiconductor. The person who has joined now, please mute yourself. Yeah. Therefore, we can say that whenever boron is doped into silicon, the resulting material is a p-type semiconductor. It's a very simple answer. So I hope this concept is clear. Yeah. So next we'll move on. So for the final answer is it's a p-type semiconductor. So next is, for an FCC metal, the ratio of interplanar spacing obtained from the first two peaks of the X-ray diffraction pattern is. So in order to understand this particular question, we need to know what are extinction rules. That is, for every type of unit cell, we will be having a set of allowed reflections and forbidden reflections. That is, when we are seeing an XRD pattern, if you have seen XRD pattern will have certain peaks, right? And corresponding to these peaks we will have HKL values, and here we can see that for a primitive or a simple cubic unit cell, any combination of HKL is possible. If the material is body centered, HKL should be even. And with respect to such materials, please note that 0 is also taken as even. And now the same, what we are need to know from the question, FCC metal. For an FCC metal, HKL should be either all odd or all even, which means that mixed numbers are not allowed. Both all HK and L should be all odd or all even. Therefore, what will be the first peak in case of an FCC metal? Like if it's an all odd combination, what will be the first set of three numbers in FCC? It should be all odd. Yeah, that is the correct answer. So first peak will be 111. And next what we can have is, what after 111, when we are taking a similar combination, it will be 200. Therefore, the first peak in FCC occurs on plane 111. Second peak occurs on plane 200. We know that the equation for interplanar spacing for a simple cubic unit or a cubic unit cell is given by A by root of h square plus k square plus l square. No, 0, 0, 0 doesn't exist, right? We need to have a plane, yeah. We need to have a plane in the material. So 0, 0, 0 is like no number is there, right? It will be just a coordinate point. It will be the origin itself. Yeah. So these combinations are for planes. So first one is 1, 1, 1, and second plane will occur to 2, 0, 0. Yeah. So it's not just a combination of numbers. These numbers actually represent planes. Therefore, if you're taking 0, 0, 0, it will just be the origin itself. We don't have any specific significant plane for that, or specific plane for that. So the first plane that occurs is 2, 0, 0. Yeah. So, and interplanar spacing equation is given by A by root of h square plus k square plus l square, where HKL denotes the plane under consideration. So, and A value is also known for the given unit cell. Now we need to find the ratio of the interplanar spacing. That is, we need to calculate D1 and D2 for both planes. So, first is for 1, 1, 1 plane. A by root of 1 square plus 1 square plus 1 square, that will be given by D1, and d2 will be a by root of 2 square plus 0 square plus 0 square. And upon taking d1 and d2, d1 by d2, we will be getting 2 by root 3. That is a by root 3 divided by a by root of 4. That will be 2 itself. Therefore, on transposing, it will become 2 by root 3. And the final answer will be 1.1547. So if we see the options, 1.1547 is the answer that we got, and in the options there is 1.15. Therefore, the answer to this particular question will be option D. Is it? Sorry? FCC diamond means in the table. Diamond cubic structure. Yeah. Means if you have seen the structure for a normal diamond cubic structure, we can see that it will be two FCC unit cell that is mixed with each other, and plus it will be having four atoms inside. Diamond cubic unit cell. So I'll show you how a diamond cubic unit cell looks in Google. So this will be the diamond cubic structure if you see. It's basically an FCC itself, but inside there will be four additional atoms. That is why it's called FCC diamond cubic structure. Is it clear? Yeah. Yeah. So in case of FCC diamond cubic, either it can be HKL should be all odd or all even. If it is all even, suppose it is a number like 200 or maybe 240, etc. There is a condition that their sum should be equal to 4 times n. Usually for gate examinations, they will ask only simple cubic BCC and FCC. FCC diamond is very seldom asked, and HCP I have not seen any questions in previous year at all. So usually it's better to remember these first four rows. Yeah. So that is the ratio, and we got our answer as 1.1547. Next is saturation magnetization of an FCC metal with lattice parameter zero point 0.2 is given as 600 kiloampere per meter. The net magnetic moment per atom is given by in Bohr magnetron we have to calculate. So that is the next question. Somebody has unmuted. Please mute yourself. Okay, somebody has posted a message. Okay, fine. So first we need to know the equation for saturation magnetization. What is saturation magnetization? Saturation magnetization is defined as the ratio of total magnetic moment per unit cell divided by volume of the unit cell. Volume of the unit cell we all will be knowing. If we have, for example, a single cubic, if FCC is given, therefore if we know the value of A, we can calculate the volume of unit cell as A cube. Next is the total magnetic moment per unit cell. We know that in a unit cell many atoms will be there, and each of these atoms will be having a magnetic moment associated with them. So the magnetic moment of all the atoms in the particular unit cell is known as the total magnetic moment per unit cell. And mu b or Bohr magnetron is the magnetic moment of one electron spin. The net or total magnetic moment of an atom is the summation of magnetic moment of all the electron spins considering their signs. So basically this question is given as we have to find the final answer in Bohr magnetron. Therefore whatever we value get for this total magnetic moment per unit cell, we need to convert it into Bohr magnetron before comparing with these options. That is why it is specifically given it should be in Bohr magnetron. So how do we find out? Lattice parameter is given and saturation magnetization is also given. So from lattice parameter we can find out volume of the unit cell, and from this given value we can find total magnetic moment per unit cell. So how is that done? So we know that there are four atoms in the FCC unit cell. Therefore total magnetic moment per unit cell is given by 4 into net magnetic moment per atom. So we are considering that as X. So we know that there are four atoms in unit cell. Total will be 4 into some value of X, where X is the net magnetic moment per atom. And volume of the unit cell is given as A cube, that is 0.2 nanometer cube. That is what we have to take. Now finding out, substituting for saturation magnetization. Saturation magnetization is given as total magnetic moment divided by volume. Therefore 600 into 1000 is equal to 4 into x divided by 0.2 10 power minus 9 the whole cube. So we get the value of x as 1.24. But it should be, care should be taken that 1.24, in order to confuse you, there is a possibility that now it's not an issue, but there is a possibility that they can give 1.24 in the option, because here no units are mentioned and you can directly write 1.24. But be careful, that is not the case. Whatever answer that we have got now, that is whatever answer we have got here, x is equal to 1.24 into 10 power minus 24 a per meter square, is in amperes per ampere meter square. This has to be converted into Bohr magnetron. So one Bohr magnetron's value you need to know. Sometimes it will be given in the question, but other times you'll have to memorize this. One Bohr magnetron is equal to 9.273 into 10 power minus 24 ampere meter square. Therefore 1 ampere meter square is equal to 1 by this value. And now we have to convert this 1.24 into Bohr magnetron. Therefore multiplying on both sides we will get 0.129 Bohr magnetron. And hence the final answer will be 0.129. So is this concept clear? Yeah. Basically, the thing is, first is you have to remember what is saturation magnetization. Total magnetic moment per unit cell into volume. Okay, saturation magnetization is given to us. Volume of the unit cell we can calculate from A value itself. Now, total magnetic moment per unit cell. We know in FCC there are 4. Therefore, 4 into some x is equal to this value. And we got x. So what is this x? X is the net magnetic moment per atom. That is what was asked in the question. So they are asking the net magnetic moment per atom, they are asking. And this is per atom, this is total magnetic moment. Therefore 4 into x, that is 4 into net magnetic moment per atom is equal to total magnetic moment per unit cell. So is any concept unclear in this particular question? Yeah. The other person in the chat, is it clear to you? Yeah. So that is the case. So next is, in an FCC crystal, the strain energy per unit length of dislocation with Burgess vector A by 2 into a family of directions 110 is dash times that of an A by 2 112 dislocation. So these are basically two families of direction that is given to us, and we need to find the strain energy per unit length of dislocation. So first we need to know the what are we know that materials have defects known as dislocations, and they have distortional energy associated with them. So how do we calculate this distortional energy? This is given by an equation, that is the elastic strain energy E per unit length of dislocation having Burgers vector B is approximately given by E is approximately equal to mu B square by 2, where mu is the shear modulus of the crystal and B is the Burgers vector. So the Burgers vector is given here like a by 2 110 and a by 2 112. But we cannot use them directly in this equation because we need to find out the magnitude of B. So how do we find out the magnitude of B? A Burgers vector B is represented as 1 by 2 110, 1 by 2 112, etc. The magnitude of the Burgers vector can be obtained by multiplying the lattice parameter, that is A, to the given vector type. So what does this mean? For example, we are considering a crystal having lattice parameter A is equal to, this is another example that is not related to a question, this is just for understanding. For a crystal with lattice parameter A is equal to 2.8 some angstrom and it has Burgers vector of the type half 1 1 1. So how do we calculate the magnitude? We have to multiply this A into the sum of squares, root of sum of squares, that is root of 1 square plus 1 square plus 1 square divided by 2. So multiplying all these values, we will get the magnitude of B. Since it is half of 111, this 111 direction is converted into root of 1 square plus 1 square plus 1 square by 2. And we will get the value of B. So is calculating magnitude of Burgers vector clear? Sorry? Yeah, for example, if in case of 1 by 111, it has given 110, then it will be 1 square plus 1 square plus 0 square by 2, because already 1 by 2 is here, right? This will be given. Yeah. Like, no, no, not like that. It will be given 1 by 2, 111. Then we have to write like this 1 by 2 as it is. We have to multiply by A and take the root of this one. But if instead of 1, yeah. No, it won't come divided by 3. It will always come 1 by 2. That is the typical way in which Burgers vector are denoted. It won't come 1 by 3. Like you, basically the thing is, this particular portion you have to substitute as it is in the equation, that is 1 by 2 is here itself, only this one we are taking the magnitude. Suppose if like a hypothetical case, suppose something comes like 1 by 3, you have to substitute 3 here, but it won't come. Whatever value is here you have to substitute here directly, then whatever is inside this bracket you have to write as root of 1 square plus 1 square plus 1 square, or whatever numbers are here. Yeah. So that is the case. So then now we have the value of B, that is the Burgers vector. Now we need to find out the energy values. Therefore, the energy equation is E is equal to mu B square by 2. Therefore, the strain energy per unit dislocation. So first one in the question it was given what all, A by 2 110 and A by 2 111. These are the two values that were given for us. Therefore, A by 2 110 will have mu mu by 2, we'll take it as it is. So b1 we are calculating, so this entire bracket thing is b1, that is a by 2 into root of 1 square plus 1 square plus 0 square. Is that clear? Yeah, mu by, yes, yes, in b we are this b1 is actually expansion like this. For b1 we have to write a into root a by 2, this 2 is already given here, right? Therefore a by 2 into root of 1 square plus 1 square plus 0 square, and this is b1 square, right? Therefore this whole bracket we have to square. Only for finding b we have to use this equation, this kind of equation. Is it clear? Yeah. Similarly for the next one, that is a by 2 111, what we will write mu by 2, and for finding the value of b2 we can write a by 2 into root of 1 square plus 1 square plus 2 square, and since it is b2 square, this whole bracket will be squared. And on dividing these two equations, that is e1 by e2, mu by 2 can be cancelled. A square can be cancelled, and 2 square can be cancelled. Therefore, root 1 square plus 1 square plus 0 square and 1 square plus 1 square plus 2 square will stay. Therefore, that what it will be, this will be 2, and this will be 4 plus 1 6. Therefore, the final answer will be 2 by 6. Therefore, we can write 3 E2 is equal to 3 times E1. Is it clear? Like the question was, we have to find out the strain energy per unit length of a dislocation with Burgers vector. This one is dash times that of a Burgers vector of dislocation for this one. So this is what we took as E1. E1 is how much? 1 by 3 times of the energy of dislocation 112. That will be the answer. Is it clear? Yeah. So this is how we find out the strain energy ratio if the Burgers vector is given. So these questions are usually asked for 2 marks in case of gate examination. So I hope it is clear. So next we'll move on to the sixth question. That is the last question for today. So that is, for an intrinsic semiconductor, the room temperature electrical conductivity is given to us. If the electron and hole mobilities are 0.75 and 0.06 meters square respectively, the intrinsic carrier concentration at room temperature is dash. So can anyone give me the equation for this particular question? In case of semiconductors, what is the equation for conductivity? The other person? Okay, okay, no issues. We can see. So the conductivity of an intrinsic semiconductor is given by sigma is equal to mu E plus mu H into E into Ni. So what are these quantities? Mu E and mu H are the electron and hole mobility. Now that is the speed at which the electrons and holes move inside the semiconductor material. E is the charge of an electron and Ni is the intrinsic carrier concentration. So we know that in case of a semiconductor material, when light is incident on them or under any external stimuli, what happens? Electron hole pairs will be generated. For an intrinsic semiconductor, that is a semiconductor which is not doped. So when we are doping a semiconductor, it becomes extrinsic, right? So for an intrinsic semiconductor, this conductivity is due to the intrinsic carrier concentration, and it will be equal to the number of holes, and that will be equal to the number of electrons, because whenever a hole is an electron is generated, correspondingly a hole will also be generated. Therefore, Ni is the intrinsic carrier concentration. So this is the equation for sigma. And if we see in this question, electrical conductivity is given 10 power minus 6 ohm inverse meter inverse is given. Electron and hole mobilities are also given 0.75 and 0.06 meter square v raised to minus 1 s raised to minus n. And whenever solving problems, please keep in your mind that you have to substitute all values in SI units itself. So that is one important thing that we have to keep in mind. And we have to find out the value of Ni. So in this question, sigma is given to us, mu E is given to us, mu H is given to us. E value we already know, that is the charge of an electron. And then we can find the value of Ni. Yeah, E into Ni, yeah. So what it will be, conductivity is given, electron mobility is 0.75 meter square v raised to minus 1 s raised to minus 1, hole mobility is 0.06 m square v raised to minus 1 s raised to minus 1. And on substituting all these values, and what it will be, Ni will be, Ni is equal to sigma divided by this quantity. So if we are substituting the entire thing and we can solve for Ni. Can anybody solve me and tell me the answer of Ni? Yeah. It will be a very huge number. Yeah. What about the other person? Is he getting similar answers? Yeah. Yeah. That is the answer of Ni. That is the carrier concentration. So usually intrinsic carrier concentration will be in the range of 10 power 12 or somewhere around that. And when we are doping this constant Ni cancel, and when we are doping, what happens instead of Ni, we will be having either Ne, that is the number of electrons will be more and conductivity will be due to electrons, or in case of p doped it will be due to the number of increase in holes. So this is for an intrinsic semiconductor. This equation is for, yeah. So the thing is here we have intrinsic semiconductor, that is the material is not doped, it is not having any holes or electrons or anything. But once the material has been doped, what happens, either the number of electrons or the number of holes will increase, and accordingly the equation for conductivity will change. So I can include a question for conductivity of extrinsic semiconductor in the next class, and I'll show you how to solve them. And there we won't be using this equation, this is only for intrinsic semiconductor. Is it clear? Yeah. So any of you like, yeah, please tell me. I think there are another sessions going on for extractive metallurgy. Like weekly, there is slot for different subjects. So subject allotted to me is physical metallurgy and mechanical metallurgy. There is another class for extractive metallurgy, thermodynamics, etc. Like actually, who informs you about the timings of these class? Okay, I think so. If you check the portal, you might be able to see like who is taking extractive metallurgy and what time slot it is. Yeah, and in case those classes are already over, I'm sure that it will be recorded and uploaded somewhere in YouTube. And you can maybe drop a mail to the NPTEL portal and asking them for the YouTube channel's link or anything like that. Like all of these videos are recorded and we will be uploading them in YouTube in case you want to see the questions again and solve them. Even for today's class, I will be recording these lectures and I will be posting it in my YouTube channel. Yeah. So I hope today's six questions are clear to you. Yeah, and the other person? Yeah. So, in case you have any additional doubts, queries, or any feedback, please do write to me at santra.pmrf@gmail.com. Like, I usually cover subjects like semiconductor or fractography, or then usually some things related to defects or crystallography, and like physical metallurgy and mechanical metallurgy. So, in case you have any additional doubts or queries, or you want any type of questions to be included, please feel free to email me at this email ID. Yeah. So, and in case for people who wants to, let me stop presenting. Like, and for people who want to actually see the previously recorded videos, I'll tell you the name of the YouTube channel, and you can see the questions that we have already done. Yeah. So it is NPTEL Interactive Sessions with Sandra. That is the YouTube channel. It usually has questions on either gate mechanical engineering and a few questions on electronic structure of materials also. That is NPTEL Interactive Sessions with Sandra. Yeah. Yeah. So this is all for today. And next week also we will be having a session. So in case there is a cancellation of session, I'll be informing you in advance. I think most probably next week I won't be able to take class. So our next class will be on 29th of December. We will be doing, yeah, so we'll be doing more questions on mechanical metallurgy and physical metallurgy. So thank you so much for joining both of you, and in case you have friends who are preparing for gate, please do ask them also to join. Yeah, thank you so much. Yeah, bye.